Welcome to Math 31. This is a lesson on curve sketching, specifically on horizontal asymptotes. So the last lesson we looked at vertical asymptotes, now horizontal. So to start this one off, we consider f of x is equal to 1 over x. So you're familiar, I think, with this basic reciprocal function. It looks like this. And with respect to there being any horizontal asymptotes, by inspection, we can tell that there is a horizontal asymptote. So by inspection, horizontal asymptote of y is equal to 0. In other words, the x-axis. And also what's going on as x increases without bound, y approaches 0. So when you start talking about horizontal asymptotes, you're really talking about what the y value is doing as x increases or decreases without bound. So in both directions, y approaches 0, from different directions, of course, but from below the x-axis or above. So that's fairly typical for a horizontal asymptote, and we can tell in this case, to formalize this, the limit of 1 over x as x increases without bound is 0, and then the limit as x decreases without bound is also equal to 0. So that's a fairly routine one, and very often you can make these calls by inspection. Now, to summarize our findings, if the limit of a function as x increases without bound is equal to some number L, and we want it to be a number, if it's going to be a horizontal asymptote, it has to be a number equal to something. Well, here's the other scenario, is x decreases without bound equal to L. We would then say that y equal L is a horizontal asymptote of y is equal to f of x. Now, as you're going to see, the most common scenario, if there is a horizontal asymptote, is that whether you're going to the left, decreasing without bound, or whether you're going to the right, increasing without bound, usually equal to the same number. But we have to be careful when we're doing this. Now, to illustrate some of this, if we looked at this diagram, there's a few scenarios that you can imagine. Like, I've got a line drawn in at y is equal to 4. Here's a possibility, right? You could have as x decreases without bound, that we're approaching y is equal to 4. We could also have, coming up from this direction and approaching. Could also have, I suppose, going down like this. Here's another example of that horizontal asymptote. And as x increases without bound, we approach the same number like that. What else could we really see? Could just have a graph like this, and then have it go up and down like this. This would be an example of a horizontal asymptote. And then the favorite of everybody is where we actually cross the asymptote and then approach it like that. So that can also happen. So it is just a line that we approach. Now, in fact, asymptotes don't have to be lines, but as far as we go in this course, we just look at linear asymptotes. So that gives you an idea of what we're dealing with. Now, the real issue is how do we identify these? Now, this was hinted at earlier in the illustration. So if you needed to find the horizontal asymptote of this particular graph, now you could just graph it to the best of your ability, but really the method is to take the limit of the function f of x as x increases or decreases without bound. So it goes back to Unit 2 with limits. And the way that I would recommend this is to do the usual limit simplification and then consider the positive and the negative versions of it, so x decreasing and x increasing. Usually it's the same number unless there's something weird going on. So you may recall that the common method is to divide or factor out each term by highest power of x well, I like to go in the denominator. If you think back to limits, it doesn't really matter where you do it. But I'll do in the denominator. So I would get, so here's my expression. The limit as x approaches plus or minus infinity, to word it like that. We divide the 3x by x leaves us with 3, and then 2 divided by x, and then on the denominator, x divided by x is 1, and then minus 1 over x. So as you take the limit, you'll see that it doesn't make any difference whether x is decreasing or increasing. This is going to be equal to 3, and then that'll be just 0, and then 1 minus 0. So this limit is equal to just plain 3. For both directions. So therefore, the horizontal asymptote is going to be y equal 3. So that's the method. That's always how you find your horizontal asymptotes. Take a look at the graph. You can see that this is consistent with what we worked out mathematically. Now, the information that we had didn't tell us whether we were approaching it from below or approaching it from above, but we find that out other ways. Now this one, the same thing, and feel free to pause me at any time to work it out on your own. I'm also going to take the limit of this one, the same method as x gets bigger or smaller without bound. I'm going to divide each of the terms by the highest power in the denominator. So that would give me, dividing by x cubed would be x there, and then 7 plus 3 over x. And once again, we take the limit. And when you do take the limit, as x gets bigger and bigger and bigger and bigger, or smaller and smaller and smaller, this is going to be 0 over 7 plus 0. So that's going to be 0. So this limit is equal to 0. So a horizontal asymptote of y is equal to 0. And in fact, you might recall that when the power on the denominator is larger than the power on the numerator, that's always going to be the case. And here's what our graph looks like now. So let's try some more. So f of x is equal to 2 to the x minus 4. Now, first off, recognize that this is not a rational function. So a mistake people make with these is they start trying to divide by a power of x when there's no denominator to divide from. So here you use simple reasoning power. And some people, when they're faced with a question like this, they just plug in larger and larger values and then smaller and smaller values. See what happens. So 2 to the x minus 4. Now this is interesting because as we do the positive version, as x gets bigger and bigger and bigger, well, as x gets bigger and bigger and bigger and bigger and bigger, this one is going to get bigger and bigger and bigger and bigger and bigger as well. So x gets, plug, even if you want, substitute in x equal 1, substitute x equal 10, x equal 100, etc. And you see what's going on. But then when you take the limit as x decreases without bound, you see something else happens. So here you try, well, I'll try x equals 0. Then I'll try x equal, say, negative 1. Then x is equal to negative 10. X is equal to negative 100. And what happens when you go 2 to the negative 100? That's 1 over 2 to the 100. And you're going to see that what your number is going to approach is negative 4. Because that number is going to get smaller and smaller and smaller and smaller. So this is kind of a Armstrong method for doing it, but keep in mind that you also know that the graph looks like that because it's a vertical exponential function translated 4 units down. So if you were to graph it, here's your vertical asymptote right there, and your 2 to the x minus 4. It looks something like this. So a horizontal asymptote of y is equal to negative 4. So in fact, the rational ones are probably the easiest because you don't have to think at all. You just, either just look at them or else divide by the highest power of x. The non-rational ones, exponential or polynomial even, require a little bit more work with it. And then like number 4, kind of the same thing. It's just a polynomial function, and you have to remember what happens with polynomial functions. X to the 5 minus 2. Really what you're concerned with is the leading term. So as you were to take if you take the limit of this function as x, let's do both separately, gets bigger and bigger. Well, x gets bigger and bigger and bigger and bigger and bigger. Well, this whole function is going to get bigger and bigger and bigger and bigger and bigger. And then as the limit as x gets smaller and smaller and smaller, pay close attention to that x to the 5, the leading term. So as a negative number is raised to the exponent of 5, it's going to get bigger and bigger and bigger in the negative direction. So in fact, this is going to decrease without bounds. So therefore, if it's not equal to a number, there's no horizontal asymptote. So we end up with a graph looking like this. Goes up forever, goes down forever. Try a couple more, nothing more. I don't know, this one here isn't going to break an awful lot of new ground, but I'll go through it. You might want to pause me and have at it yourself. But here we are, just another illustration of taking a limit, basically. We take divide by the highest power of x in the denominator, which is just x to the 1, so that's going to be 2x to the 3 plus 3x squared plus 1 over x, and then that'll be x divided by x is 1, so negative 1 minus 1 over x. And I haven't decided yet whether I need to do this separately or not. But in fact, what's going to happen is the numerator, if you pay attention to this 2x to the 3, it's really just interpretation. This is going to get bigger and bigger and bigger as x gets larger. This function 2x cubed. Now watch what's happening with this one though, because as x gets bigger and bigger and bigger, 2 times x to the 3 is going to be equal to an increasing number. However, we're dividing by negative 1, so you might even want to indicate that there. This really is 2x to the 3 plus 3x squared plus 0, if you like, over top of negative 1 minus 0. So in fact, for this function, the limit as x gets bigger and bigger and bigger is going to be negative. It's going to go down. Positive number on top, and then a negative number on the bottom. And then when you take the limit as x gets smaller and smaller and smaller of this function, you'll see that your numerator, well, 2x cubed is going to be a negative number, and increasingly further to the left on the number line, but then the negative on the denominator is going to give you a positive number. Now, in fact, this doesn't really answer the question, because you weren't asked to find out what the limit was specifically, just in terms of it being an asymptote or not. So there is no horizontal asymptote. And we actually don't expect them when the degree is higher in the numerator, right? Because the numerator is going to increase, increase faster rate than the denominator. Now let's do one more, and then I think that'll probably take care of this. Here we've got kind of a messed up looking equation. I didn't graph either of these last two, but feel free to put them into your calculator. Remember, the method with these ones is when you're doing limits, the easiest way probably is to put it both underneath the radical. So you note that x to the 4x squared is equal to the square root of x to the 4, and then you have x minus 1. So when you take the limit of this function as x increases or decreases, this is what you're dealing with. Now you can handle this a number of ways. Some people like to take the square root outside. Others just mentally keep track of it. But what's going to happen within that expression, x4 over x minus 1? Well, we divide by x, and so this becomes x to the 3 over 1 minus 0. And then we stop and think. This is going to be x to the 3 over 1, which is just x to the 3. So really this question is the limit as x increases or decreases without bounds, and then you can take the square root of this if you want. So if you did the positive one, and I'm doing this one about as slow as you can possibly do it, most of you would have come to some conclusion before this, but x gets bigger and bigger and bigger and bigger, and the y value is also going to get bigger and bigger and bigger. Now the fact that you're taking the square root of it is going to slow it down, but it's not going to change the fact that this thing is going to increase without bound. And then the same thing being true as x, or a very similar thing, as x decreases without bound. This x decreases, decreases, and decreases. Now this is interesting, because this graph, in fact, this would have been obvious if we took a close look at the function to start with, but this graph has a restriction on the domain. X has to be greater than 1. So there is, this graph does not, is only defined starting at all x values greater than 1. So there is limit cannot be taken as x gets smaller and smaller. So that also just supports what we saw already, that there's no horizontal asymptote. So I didn't graph this one, but please take a look at it on your calculator. So horizontal asymptotes give you extra information about the graph. So far we've got vertical asymptotes, we've got the regular domain and range type of thing, giving us information about the behavior of the graph, characteristics of the graph at certain points. We've got first derivative analysis, which will tell us whether it's increasing or decreasing. And soon we'll be taking a look at second derivative analysis, and then we start to get a better picture, and we're able to graph virtually anything that we can differentiate. But that's it for me, so thank you for your time.